tends to expand. It changes its size. I get me now? And that's that for that. Another property of heat that we have is that heat can cause a change in temperature. That's very, very normal. It can cause a change in temperature. And since it can cause a change in temperature, we know that automatically temperature has a direct effect on pressure. That means it can also cause a change in pressure. Heat can also cause a change in chemical properties. Chemical properties. Are we there now? So these are basically some of the effects of heat. Let's now look at the definition for temperature. So temperature. Now, when we hear the word temperature, we can say it's the degree of hotness and coldness of a body, like we actually do here. But we know that temperature is actually a measure of kinetic energy, because the more you heat a body, the temperature tends to rise, and then you find out that molecule tends to gain enough kinetic energy to be able to move. So we can also say that temperature is the measure of the degree of kinetic energy of the body. You understand? So we are saying that it is the measure of the average kinetic energy of a body. So that's it. It is the measure of the average kinetic energy of a body. So to say, also can say it is the hotness or coldness of a body. Good. I know that temperature is measured making use of what we call the thermometer. We have the thermometer, and we have different kind of thermometer. We have the liquid in glass thermometer. We have the solid thermometer. And basically, whenever you hear the solid thermometer, liquid thermometer, they are majorly dependent on their thermometric fluid, or their thermometric substance rather, their thermometric substance. So when the thermometric substance, which is the substance that responds to the heat change in a measured or graded way, when that substance is a liquid, then you can call it a liquid thermometer. That's why we're talking about mercury in glass thermometer, MIG, and alcohol in glass thermometer, AIG. These are both liquid in gas thermometer. Are we together now? So that's basically it. Then we will now look at the different scales in which we use to measure temperature. So we are looking at scales used in measuring temperature. These are JUPEB concepts that you must understand, measuring temperature. So what are those scales we use? There are three major scales you must keep in mind. We have the Kelvin scale, we have the degree Celsius, and we have the degree Fahrenheit. Now, the Kelvin is just K, degree Fahrenheit is degree F, and this one is degree Celsius. There's something we call scale intervals that you must know for each of them. We have the upper fifth scale and the lower fifth scale. Your upper fifth scales are what you represent up here. So I can just put it upper fifth scale, upper fifth scale, upper fifth scale. I'm doing the upper fifth scale for both Kelvin, degree Fahrenheit, and degree Celsius. Now the upper fifth scale is simply the temperature at which the substance boils. So that's simply called the steam point or boiling point. So that's it. So the upper fixed point are the steam point or boiling point. Are we together now? While the lower fixed points are what we refer to as the what? As the ice points or freezing points. And it is not still wrong to call it the melting point. And for the Kelvin, we have what? We have 373 Kelvin as the upper fixed point, while the lower is 273. These are constants you must know. The degree Fahrenheit upper is 212 Why this one is what? Why the lower is what? 32. Then for this other guy here, degrees Celsius, we have 100 up and we have 0 degrees Celsius down. So you must know those scales. Then when we now talk about scale interval, the scale interval is simply the difference between the upper fixed point and the what? Lower fixed point. Are you there now? So when we look at the scale interval for your Kelvin, it's simply 373 minus 273, which gives you 100. So you can say the SI of Kelvin is simply 100 Kelvin. You understand? That's 100. Then when we look at the SI of degree Fahrenheit, it's simply saying 212 minus 32, which gives us 100 and what? 80. 180. Then we have the SI of degree Celsius, and that will give us 100 minus 0, which is what? 100. Now let's quickly dive into what we call the interrelationship between scale. Interrelationship between scales. The interrelationship between scales. So what are the interrelationship between scales? How do we determine relationship between one scale and another scale? There we make use of a particular technique. So let's take, for instance, we want to check the relationship between the degree Celsius and the degree Fahrenheit. In this case here, we will make use of our scale lines such that at one side you put the property or the scale values of one of the temperature scales. For example, now degree Celsius can be written here and degree Fahrenheit at this region. What's the upper fixed point of degree Celsius? We have 100. The lower fixed point of degree Celsius is 0. Upper fixed point of degree Fahrenheit is what? 212. And the lower fixed point of degree Fahrenheit is what? 32. Automatically now, we have represented them in our scale conversion line. Now, we are going to consider a point along between the upper fixed point and the lower fixed point, which is going to be unknown. And we'll look for how one scale, the scale of the degree Celsius, tends to relate to the scale of the degree Fahrenheit. So I will represent this unknown region as degree Celsius and this place as degree Fahrenheit. What am I trying to say? If 100 degrees Celsius is 212 Fahrenheit and 0 degrees Celsius is equivalent to 32 degrees Fahrenheit, then what should be an unknown value of degrees Celsius in Fahrenheit? That's what we are looking at in the conversion. So in that case now, all you need to do is this middle value subtracted from the lower fixed point divided by the upper value subtracted from the lower fixed point, and you repeat that same process here and equate them. So what am I saying? Automatically we should be having degrees Celsius, minus what? 0 divided by 100 minus 0. Automatically, you know that in the denominator here, what we are actually getting is called the what? Scale interval of your what? Of your first. You can call that the standard scale. You understand, which is the one that we have when solving. Then we will say it's equal to what? It's equal to, repeat the same procedure again. We did this minus this divided by this minus this. In this case now we will do what? Degree Fahrenheit minus 32 divided by what? 212 minus 32. And then in this side here, what are we going to be having? We'll be having 0 degree divided by 100. And then that will be equal to what? Degree Fahrenheit minus 32. Mathematically, we know we can't subtract these two things. Then 212 minus 32 gives us 180 is the scale interval. Cross multiply, then you get what? 180 degrees Celsius is equal to 100 degree Fahrenheit minus 3200. Let's say we now want to make degree Celsius or degree Fahrenheit rather the subject of formula. If I'm making degree Fahrenheit the subject of formula, that means I want to bring out an expression that will enable me convert degree Celsius parameters into degree Fahrenheit values. So in that case there, we'll be having what now? We'll be having 100 degree Fahrenheit to be equal to 180 degrees Celsius plus 3200. This is just simple algebra. And then what are we going to be having? Divide through by 100 to make the expression very simple. So when I divide through by 100, are you there now? What are we going to be having? Degree Fahrenheit will be standing alone as the dependent variable here now, which will the subject matter. And then this one here will give us what? 9/5 if we did that correctly. 0 cancel 0, 2 can go in here 9, 2 can go here 5 degrees Celsius plus 32. This is how you get relationship between scales. So it does not work only for degree Fahrenheit and degree Celsius conversion. It's simply a technique that you will eventually use whenever you are converting from one scale to another. It is very sure for you to see this kind of questions in your JUPEB. Very sure, it's certain that you will see them. So here now, what we're just doing is that we're analyzing the concept. So very soon in one of our videos, you will still see where we're going to be solving and analyzing questions from both the recommended text and past questions. You'll be seeing probable questions that will be coming out even in the next JUPEB exam. So good. Let's now look at what this statement implies. It means that if we're given a question that tells us that we should convert, for example, convert 20 degrees Celsius into degree Fahrenheit. All you just need to do now is to insert or substitute this 20 degrees Celsius as the value for degree Celsius here, and then you solve. That will give you the answer to the question. So we're having degree Fahrenheit therefore should be equal to what? 9/5 times 20 plus 32. And that gives us what? Degree Fahrenheit equals to 5 here 1, 5 here 4. 9 times 4 should be giving us how many? That should be giving us, if I'm not mistaken, 36. So I'm having 36 plus 32. And then we're having degree Fahrenheit equals to what? 68. So it means that 20 degrees Celsius is equivalent to 68 degree Fahrenheit. That's the meaning. So the expression here helps to get this value. But let me advise you, as scientists, do not cram relationships. That is why I showed you the technique with which we use to arrive at this relationship. So sometimes they might be giving you questions where they are going to be relating probably a resistant wire thermometer or resistant thermometer with a degree Celsius. You have to make sure you still apply the same thing. First thing to do, identify upper and lower P scale of the first temperature scale, then compare it with the temperature scale that is standard, that is given. You understand? So that is that for this analysis here. Now, based on what we have there, we'll be entering into what we call heat capacity and specific heat capacity. Heat capacity, heat capacity, heat capacity, and specific heat capacity. This is a very, very interesting concept. It is very, very direct. Let me do something quickly. Let's imagine we have a solid that we've been able to magnify such that it has, it contains different units that are identical. Different identical units. So what am I trying to say? Let's say this box is identical to every other box within this place here. So automatically we know within our mind that the total number of boxes I have here is 1, 2, 3, 4, 5, 6. Then when I do the same thing here, 1, 2, 3, 4, 5, 6, 7. So it's just 6 times 7, right? And that gives us 42. So I know that I have 42 boxes here. Now, we are going to be looking at two kind of things. If they ask us for specific heat capacity, we are just talking about what amount of heat will be needed to raise just one of these boxes. That's a unit mass. Will be needed to raise a unit mass of this box temperature by 1 Kelvin. That one is talking about specific. But what's heat capacity? What amount of it will be sufficient enough to raise all the mass by 1 Kelvin? Now, if you are thinking deductively, you should be able to infer as a science student that what? If you use 10 joules of heat to raise this unit mass by 1 Kelvin, automatically, how many joules of heat you use to raise everything? That will simply be the number of boxes here times the one for raising one, which gives you 420. This value here is the heat capacity. Why this one that was able to raise just this one is the what? Specific heat capacity. So this is just a very mundane way to just explain, very normal layman kind of explanation of the concept. Now let's be scientific here. If we are told to define specific heat capacity can be defined as the amount of heat required to raise a unit mass. That's the key word they are looking for there. A unit mass of an object by 1 Kelvin. Now, 1 Kelvin change is equivalent to 1 degree Celsius change. That's why some textbooks will use the word by 1 degree Celsius. So they are still the same thing. So I'm going to put slash here, or by 1 degree Celsius. That is specific heat capacity. And it is represented by what? It is represented as small letter C. As small letter C. And it is measured. I won't tell you what it's measured in. One of our videos contains a concept from Physics 001 topic 1, which is unit and measurement. And it teaches you how to be able to determine the unit of certain parameters. Good. By derivation. Now look at this. Given that H is equals to MC change in theta. This is a common formula that I'm sure you have come across in secondary school. Now, the C here is your specific heat capacity, M is your mass, this is your change in temperature, right? Good, and H is your heat. Let's make this specific heat capacity the subject of formula. Then what will be having? C will now be equals to H all over what? M change in theta. Then, what should be the unit? We know that H is measured in what? In joules, right? So it means that this is joules divided by mass is measured in kilogram, and temperature change is what? Kelvin or degrees Celsius. Automatically, we are saying that the unit of specific heat capacity is what? Is joules per kilogram per Kelvin. Joules per kilogram per Kelvin. That's the unit for specific heat capacity. How about your heat capacity? Remember that I said that heat capacity is usually obtained by multiplying your what? By multiplying your specific heat capacity by the total boxes. That total box is like saying the total mass. Are we getting it now? So we are saying that heat capacity, first of all, is the amount of heat required to raise the whole body, to raise the temperature of the whole body. You are raising the temperature of the whole body, by what? By 1 Kelvin. So in that case now, like what we said now, by deduction, this one now is represented by a capital letter C. It is denoted by capital letter C. Some textbook will use C subscript P. Anyone that goes or work for you is fine. Nobody is checking your representative symbols. All they are checking is your what? Is your physical accuracy and analysis. So now we've been able to get what we denote it as, and we've been able to infer that that heat capacity usually is equal to what? The mass, total mass multiplied by the heat required to raise a single mass, which is the heat and specific heat capacity. Now recall that what? That we said this specific heat capacity, small letter C, is equal to what? H over m change in theta. Let's now substitute that parameter into this expression here and see the implication on the mathematical expression. And that will be giving us what? We are having C is equal to what? M times H divided by m change in theta. Now m cancels m, and then we have an expression for our heat capacity. And what does that give us? Tells us that heat capacity now is equal to H divided by change in theta. What is the unit of this deduction? What is the unit of this deduction? It tells us that this guy is going to be measured in joules per Kelvin. Joules per Kelvin. That's the unit for your specific heat and for your heat capacity. That is the unit for your heat capacity. So these things are very, very simple. There is no complexity in them. It's very, very direct. They are derivational and they have easy application when it comes to solving. Now the next thing we are going to look at under the same thing is experimental methods in determining the specific heat capacity of objects. So we want to look at it now. Experimental model. Experimental models in determining the specific heat capacity, of objects. So good. We have experimental models. So we are going to be looking at the obtaining or deducing the specific heat capacity of objects by method of mixture. We are going to be looking at by method of mixture. We are going to be looking at by electrical method, and then we are going to be looking at mechanical method. This is where we introduce us to a phenomenon that we call Newton's law of cooling. Now, in this method of mixture, there is a basis for this experimental model that we must not forget. And what's that basis? We are mixing two materials together, one that is very hot and one that is very cold. That's one that is thermally dense and one that is thermally less dense. It is very, very imperative that we are able to deduce or recollect that what? When two objects of different temperature are mixed together, the hotter material will actually be transferring heat to the what? To the cold substance. Are you getting me now? And then we can now deduce that what? That means the heat that will be lost, heat lost by hot substance should be equal to the what? Heat gained by the cold substance. That's exactly what we are talking about there. The heat lost by hot substance should be equal to the heat gained by the cold substance. So good, that's method of mixture. Let's now describe the experimental process, because in JUPEB they will tell you with the use of an experimental analysis, describe the method used in obtaining the specific heat capacity of an object. You understand? So you're assuming you don't know the specific heat capacity of that object, and now you want to use an experimental model to deduce it. So that's what we're going to be describing now. So I'll be explaining the methodologies quickly, but when you are presenting this kind of answers in your JUPEB, you have to make sure you follow your A square MOC. That is, you have to first of all write the aim of your experimentation, which is to deduce the specific heat capacity of the ball or object, depending on what the question is presenting. The next thing is the apparatus. You have to be able to remember that you make use of a calorimeter, you make use of a stirrer, you make use of water as a material, you make use of the Bunsen burner or a source of flame to heat up the ball, and then you also make use of what? You also make use of the ball itself. That's the material that you're trying to deduce its specific capacity. You should be able to state all those things before you now start describing your method. But now, I want you guys to look at something now. Let's quickly use models to illustrate a lab kind of activity. So let's imagine we have a ball. We have a ball like this, and this ball, we heated the ball. We heated this ball, let's say with the help of a Bunsen burner or a candle or whatever. So we heated this ball, and obviously you agree with me that there will be a point this ball will now be very hot. So I will call this one now hot ball, which is my aim. You understand? I need this ball to be very hot. So at this point where this ball is very hot, it has a temperature, which I'll just call theta B. I'll just call that theta B. So let's call it theta B, temperature of the hot ball. You've heated the ball to a particular temperature, so we have theta B, temperature of the hot ball. As we were heating this substance, let's now say we already had prepared our calorimeter, which is going to be light properly. Our calorimeter. So this is the calorimeter here. We measure the calorimeter to know the mass of the calorimeter. Very, very important. So let's say the mass of the calorimeter here, we'll call it MC. So mass of calorimeter. You know this ball already has its own mass too, which you can call mass of the ball. The specific heat capacity of the ball is what we don't know, which we need to deduce. These two here can be measured. You can get the mass by using the mass a weight balance. Are you getting now a weight scale? And you can get the temperature by making use of the thermometer. Same thing in this case. So by the time we have this calorimeter here, what we'll do now is we have to find the temperature and the mass of this calorimeter. Are you getting now? Then we will introduce water into the calorimeter. So when we introduce water into the calorimeter, we have an image like this. We have an image like this. So good. Normally you have this stirrer inside the calorimeter. Good. So here now we are having mass water here. So if you put this thing on the mass scale, what you'll be getting as your mass is both the combined mass of the calorimeter and the what? And the water. But you know what to do. By the time you have the scale of the calorimeter and water, and you already had the initial scale of the only calorimeter, to get the mass of the water is just to subtract. So automatically here, I'll come here and write that we now know the mass of the what? Of the water. How did we do that? We subtracted the combination mass we subtracted the mass of calorimeters only from the combined mass. So good. Now that we have this one here, the next thing in the experimental method now is to now create the mixture. But before we even talk about creating the mixture, we know that whenever two objects have been in contact for a long period of time, they must equilibrate. They must have a common temperature. Why? Because they would have been exchanging heat amongst each other. So there will be a point they will equilibrate. So this point when they equilibrate is where they will have what we call their temperature. Let's call that temperature theta 1. So theta 1 is the temperature of the water inside. It is also the initial temperature of the what? Of the copper calorimeter or the calorimeter per se. Good. Then we will now introduce the ball. We will now introduce this ball into, or immerse this ball into this water that is in the calorimeter. What do you think will happen by the time you introduce it into the water and start stirring? You agree with me that this is the point where the ball will lose heat, because you have put it inside water that was cold or just normal or at room temperature. I get it now. This is the point when it's going to lose heat. let's say you start losing it and you start stirring it, there will not be a time after a long period of time that also their temperatures will equilibrate. There are principles that explain this process where these guys have to equilibrate, like Zeroth's law and all those kind of stuff. But we are not going into those ones now. This will be later along our thermal physics playlist. So good. This one now equilibrates and gives us a new temperature, which we call in temperature of the mixture. I believe that if you are really thinking, you are agreeing that in this whole experiment, the highest temperature ever measured was the temperature of this ball after heating, that is when it was still very hot. Then this temperature of the mixture should actually be higher than the temperature of the water and calorimeter combined, because the temperature of the mixture happened when you put the hot ball in this water, and that hot ball obviously raised the temperature. So this is the highest temperature, followed by this one, and followed by this initial temperature of both water and this thing. So good. Now that we already know our experimental method, what's the mathematical implication of what we have just done here? We can now see that the heat loss by ball should be equal to the what? Should be equal to the heat gain by what? By water, who also gain the heat? Calorimeter. Those are the two things that gain the heat. Heat gain by water and heat gain by the calorimeter. Are you getting me now? And remember that we said when we are dealing with heat in specific capacity, we leverage on this formula here. So heat, whether lost or gained, is usually equal to MC change in theta. That's what we're going to use to represent each of these guys here. So each of these people here, we are going to use that formula to represent them. And what does that mean? Heat loss by ball. Let's focus on the ball using this thing now. So that means the heat loss by ball should be mass of ball times specific heat capacity of ball, which is what we are looking for, times change the temperature of the ball. Good. So the mass of ball here is MB, specific capacity of ball CB, change the temperature of the ball. What was the hottest temperature of the ball? This was theta B. Are you there now? And what was the next temperature when the temperature of the ball reduced? It was this theta M, because all of them had this theta M. Water, final temperature of water is theta M. Final temperature of this calorimeter is theta M. Final of the ball is theta M, because when they put the water, they equilibrate at that temperature. So I'll come here and write theta B minus theta M. Normally, heat change is supposed to be final temperature minus initial temperature. But since we are looking at it in terms of loss, that's why we have to reverse that subtraction process. We're not using the final temperature because that's the hotter one minus the initial temperature. So that will be equal to what? Heat gain by water. Follow water now for this same thing. That means we'll be dealing with mass of water times specific capacity of water times the temperature change in water. So that's MW times CW multiplied by temperature change in water is what? This is the final temperature of all of them. I mean, that is both water itself. So the change in temperature of water is theta M, that is temperature of the mixture, where water is also present, minus what was water before? Theta 1. I wrote it here. Both water and the calorimeter had the same temperature. So theta 1. Plus heat gained by calorimeter alone. That one is what? MW, MC, that is mass of the calorimeter, multiplied by specific heat capacity of the calorimeter, which will also be known. Then multiplied by heat change by calorimeter. The heat change by calorimeter is usually the same thing as heat change by water. Why? Because both of them were in the same single state of condition, that is thermal condition, along the whole experiment. So what's the final temperature of the calorimeter when they added the ball and they equilibrate? Theta M. So we have theta M minus what? Minus the initial, which is what? Theta 1. So this is an expression here. This is the general expression on how to be able to obtain the specific capacity of that ball. You know, this is our point of interest here. So having that there, we can solve for that. What's common in both of these expression? Theta M minus theta 1 is in both of them. So we can come here now and say therefore, MB CB, we are rewriting what is there, theta B minus theta M. We can say it is equal to what now? Factorize. What's common in both sides? Theta M minus theta I is common in both sides. And then what is left behind? MWCW. This is basic maths. We have a playlist that contains factorization. If you have a problem what we are doing here, you can actually watch that video on factorization. So in science, every knowledge starts as a prerequisite to the next. So we are looking for CB experimentally. Experimentally, CB we are looking for. So what do you do now? You have to make CB the subject of formula. So CB therefore should be equal to, you just have to divide both sides by every other thing that is not CB. And then you'll be having theta M minus theta 1 into bracket MW CW plus MCCC divided by what? Divided by MB theta B minus theta M. So this is the general expression that will be used in determining the specific capacity of the unknown ball. This is by method of mixture. But by electrical method here, by electrical method, what we are doing now is we have an electrical source. We have an electrical source that is supplying, keyword is supplying, that is supplying heat energy to another object or another body. So what do we do in that case? All we need to say is that heat supplied should be equal to what? Heat gained. This one is very direct. The problem is the heat supplied is in form of electrical energy. Electrical energy. So you really need to be able to remember all the formulas of electrical energy to be able to do what? To be able to expand the formula. So in that case there, what am I going to be having? I'm going to be having heat formulas, that is energy done within a heat system or an electrical system rather, and I'm going to be equating it to my heat gain, which is I'm equating it to the MC change the theta formula. And there I'll be having IVT, remember, I'll be having I square RT. We are saying that this one here is equal to what? I can also have PT. We are saying that this one equals to what? This one equals to MC change the theta. Same for this one, MC change the theta, and same for this one, MC change the theta. So it depends on how the question comes in this case. Sometimes they will give you the current, the resistance, and the time. In that case, you are using this part of the formula. When they give you the power and the time, you are using this last one. When they give you current, voltage, and time, you are using this one up here. So that's exactly what electrical method is talking about. Sometimes they can even interrelate it with mechanical system. Mechanical system. So when they relate to mechanical system, all you need to remember is that we have two major kinds of mechanical energy, which is what? Kinetic energy and what? Potential energy. When we are looking at it from the perspective of kinetic energy, we are saying that 1/2 mv squared is equal to mc changing theta. And what's the implication? M cancels m here. So we are going to be having what? We are going to be having what? Make C the subject of formula. Let's say we want to get the specific capacity. So what will C be? So I'll be having C to be equal to what? C to be equal to V squared divided by 2 change in theta. Right? That's what we're going to be having. V squared divided by 2 change in theta. So sometimes physics can come out in any method, in any manner. You have to be ready for such questions. Potential energy here is what? MGH. So we can also say MGH is equal to what? Is equal to MC change in theta. So when the question comes out in this form here, we know that M can also cancel M. Let's make C the subject of formula from this one. So we'll be having what now? We'll be having C is equal to what? GH over change in theta. So that's what we're having. GH over change in theta.